a great honor being here, and it's also a great pleasure being back at Cambridge after so long a time. I've studied here quite a few years ago. Waveform knowledge is essential to a lot of the great results you were hearing today about LIGO, both in the morning session and the afternoon session. LIGO detects signals with matched filtering, which requires to know the templates to build your template banks. Parameter estimation is done by comparing the detector output, the observed data, with the expected waveforms for a wide variety of black holes with different masses and spins, and essentially mapping out for which masses and spins the data is consistent with the expectation. And testing GR, well, you need to know the prediction of GR if you want to test it. So the waveform modeling is, in a sense, that the basis on which all the physics and astronomy of the gravitational wave detections actually builds, that is described in Pablo's talk and in the talks later on. And of course, also the little detail of actually needing to build a detector and making it work. So this talk is about binary black holes orbiting and colliding with each other, and how to compute the waveforms from them, and how to do so accurately and comprehensively for any region of parameter space, any mass ratios, and eccentricity. There's a few different tools we have available to do so. For the in-spiral phase of the binary, the oldest and most well-known tool is post-Newtonian theory, a perturbative expansion in V over C that has been pushed to remarkably high order by now. Here's one example, the orbital phasing as a function of the frequency, up to 3.5 post-Newtonian order, V over C to the 7 terms. By now, the first V over C to the 8 terms arrive in the calculations. This is the non-spinning one, and if you go through post-Newtonian papers, it's quite easy to find remarkably complicated expressions, like this one that extends over 3 pages in Luc Blanchet's Living Review article. So that's one of the tools available. At the opposite end of the spectrum, for the ring down, black hole perturbation theory is an important tool that essentially yields the quasi-normal modes of the black holes, frequency and decay rates as a function of black hole spin. In the middle, bridging the in-spiral to the ring down, is numerical relativity. Besides the in-spiral to ring down axis, there's also another important axis, that's the mass ratio. And as you go towards more extreme cases, another tool that's available is perturbation theory in the mass ratio, leading to the cell force results of the little black hole gravitational waves acting on itself, and that way modifying its orbit. All these tools have different regions of parameter space where they are applicable. And the one that's most interesting for me for today is numerical relativity, for the one reason because that's my area of expertise, but on the other reason because this is precisely where the LIGO gravitational wave detections so far have been happening. Mass ratio quite close to unity, and the total mass of the system such that the late in-spiral, merger, and ring down are all important for the analysis. In the future, bigger parts of this parameter space will become important. I and many other people are hoping desperately to see black hole neutron star binaries in the near future, or binary neutron stars. The mixed binaries are at higher mass ratio. And the LISA systems, of course, are all over the place. Supermassive binary black hole mergers are, again, up here in the upper right corners, mass ratio 1 to perhaps mass ratio of 100. And extreme mass ratio in spirals can go all the way down to mass ratio of 1 to 1 million. Especially for LISA, but also for the mixed binaries, the spin of the black holes and the eccentricity become ever more important. So we also need to take into account those dimensions of the parameter space as we move forward. Okay, let me move on and actually put in some more details about numerical relativity, realizing that this is a very mixed audience that may not know a lot about it. As Pablo already pointed out, numerical relativity is quite a complex subject with a long history, dating back all the way to the 1960s. And in 2005, 2006, the big phase transition happened, where it became possible to simulate binary black holes colliding with each other. First, the work by Franz, and then shortly thereafter Campanelli and Baker, as well as the results of the SXX collaboration that I'm mostly discussing today. The very first simulations showed already very clearly merger and ring down signals. So here's Breteau-France's work and Baker and Campanelli. And very quickly, the simulations became longer with more and more in-spiral orbits being added. Here's a result from 2007 with about 5 orbits. And one very important early result of these very first simulations was already the simplicity of the merger. It is a continuous transition from in-spiral to ring down. And it's that simplicity that makes it possible to consider modeling waveforms for binary black holes in the exquisite detail we can do today. Pablo already pointed out the 2 different approaches of simulating binary black holes. It's actually quite interesting because the 2 approaches are making orthogonal choices in essentially every single step of the setup. The type of initial data is different, puncture initial data versus quasi-equilibrium. The type of evolution system is different, BSSN and harmonic. Pablo already explained these 2. The coordinate conditions are different. The boundary conditions are different, and the numerical techniques being used are different. Finite differences with adaptive mesh refinement versus spectral methods. So there's these 2 very, very orthogonal approaches to simulating black holes. Let me highlight a few aspects of the whole thing to give you a flavor of all the considerations that go into these codes. This is not meant to be exhaustive or comprehensive in any way, but just, as I said, giving you a flavor. The first step is to solve the Einstein constraints in order to get initial conditions that actually satisfying the Einstein equations. The usual trick is always to do a conformal transformation on the spatial metric, and this turns the Hamiltonian constraint into an elliptic equation for the conformal factor. The more interesting part is what to do with the extrinsic curvature, and especially with the trace-free part of the extrinsic curvature. So over the years or decades, the combination has emerged of a conformal scaling of the extrinsic curvature and a transverse traceless decomposition. The latest twist in the saga was introduced in 2003, namely this weight function here for the transverse traceless decomposition. And with this weight function that also conformally scales with psi to the 6, it turns out the conformal scaling and the TT composition commute with each other. And so now, no matter which one does first, one arrives at a unique conformal transverse traceless decomposition down here in this corner, which then turns the momentum constraint into an elliptic equation for the vector potential in the extrinsic curvature. The weight function also unifies the Hamiltonian picture and the Lagrangian picture of the initial value problem, by the way. Okay, so far for the theory. And now all the practicalities for binary black holes. You need to think about the asymptotics and the boundary conditions for the elliptic equations being solved. There's 2 different approaches. One is just solving the Hamiltonian constraint for the conformal factor. That's the puncture data. And the other one is more comprehensive and solves the 4 4 constraint equations plus 1 equation for the Lapse function. You need the codes to do so in an elliptic solver. High spin also requires extra work because the naive and simple approaches get you only up to spins of about 0.9. Sounds great, but a spin of 0.9 only represents about 60% of the rotational energy of an extremal Kerr black hole. So if you want to study extremal black holes, you need to do much better. And so by now, initial data can be constructed up to spins of 0.9995 approximately for rotational energies of about 99% of the maximum rotational energy. Finally, you need to think about controlling the eccentricity of your simulations. If you just make your best guesses and you begin evolving, you typically find a separation of the black holes like this black curve here, which is inspiraling as it should be, but it has an overlaid eccentricity. Field binaries are expected to have essentially 0 eccentricity because during the post-Newtonian inspiral, eccentricity is damped away very rapidly. And so techniques had to be developed to take this eccentric inspiral and analyzing it and correct back the initial data to get the smoother 0 eccentricity initial conditions. A lot of work has also been spent on the evolution equations. Pablo already went over this, and perhaps Franz is talking more about this, so I'm going to skip it and go straight on to giving a few details of one of the codes being in use to simulate binary black holes, the spectral Einstein code. The word spectral refers to the fundamental approach of expanding solutions in terms of basis functions, Chebyshev polynomials or spherical harmonics. One big advantage of this is because you know your basis functions analytically, you can compute derivatives analytically and are not incurring any errors with finite difference stencils, for instance. Another advantage is going to become clear later, the very high accuracy of these types of methods. This code was developed by the Simulations of Extreme Spacetimes collaboration, which got started at Cornell and Caltech and has since then expanded to about 7 or 8 institutions over the world. This has coupled the spectral methods to a multi-domain method where we have spherical shells near each black hole, cylinders in an intermediate distance, and then at large distances, more spherical shells. So reasonably complicated. Because the Chernowski harmonic system actually has all characteristic speeds within the light cone, we can employ black hole excision, taking advantage of the light cones having tilted over inside the black holes. And at the artificial boundaries inside the black hole horizons, the red surfaces here, we actually do not need to put any boundary conditions. At the outer boundaries, we use constraint preserving and minimally reflective boundary conditions. Both of these are important because the long simulations are actually cause the outer boundary to be in causal contact with the strong field region. It was already touched on moving coordinates. Because of the black hole excision, we're actually rotating our entire coordinate grid along with the two black holes, and we're also deforming the inner regions to adjust to the shapes of the horizons. Here's some case just before merger showing how much deformed the black holes actually are. And putting all these things together, you can make the most important output of the calculations, nice movies. Here's one that we did in 2009. Equal mass non-spinning black holes happily orbiting around. The big plane represents the orbital plane, color-coded by the Labs function. Up here in the trajectory, so you see very nicely the almost perfect spiral pattern that arises because we reduced eccentricity. The black holes merge and eventually ring down into a quiescent black hole. For today, the important part are the waveforms. And so here's another plot of the waveforms showing, again, the in-spiral merger ring down. On the log y-axis, you see very nice the exponential decay during the ring down phase. And in fact, the numerical relativity quasi-normal modes agree with the perturbation theory prediction for the frequencies to about 0.05%. The important part here, though, is the right-hand side panel, the accuracy of our simulation, the estimated error in the gravitational wave phase. At low resolution, this is about 1 radian. As we go up in resolution, it gets better by about a factor of 100. And the two important points here is that we're only increasing resolution by a factor 1.5 along each dimension. And this very rapid increase in accuracy is due to the spectral methods. The other point to note is that even at low resolution, we're already very good at having very small errors. And this is due to the moving grid approach, where the black holes are actually not, we don't have to advect the black holes through the grid and that way pick up advection errors. Okay, now we can begin to do some science. Here's a very early comparison between post-Newtonian and these accurate numerical simulations. We are aligning post-Newtonian and numerics at about 20 cycles before merger, and then monitor the disagreement with post-Newtonian as you go earlier and later. At the second post-Newtonian order, you see, even going earlier, you find quite noticeable differences, so that's definitely not good enough yet. And as you increase post-Newtonian order in this comparison, you see that there's actually very nice convergence, confirming and cross-validating post-Newtonian results and the numerical simulations against each other. You might even be tempted, if you don't look very carefully, that you see that find almost perfect agreement between post-Newtonian and numerical relativity, until you begin changing around a few of the ambiguous knobs in post-Newtonian theory and realize that some versions work well, others don't so well, and there's no a priori knowledge which one actually are working. This turns out to be the best possible case for post-Newtonian, equal mass, known spin. As you put in unequal masses or spins, post-Newtonian theory becomes less accurate. Here's one example, increasing the mass ratio from 1 to 1/6, and you see that the errors go from order 0.01, where we want them to be, up to about 30. So it becomes bad very, very rapidly. Now let me turn over and actually begin to work towards the gravitational waveform models that Gabi will be using in her talk in LIGO, so you actually have some understanding of where this information is coming from. All these waveform models are basically constructed with the same basic ideas. You take analytic results for the early in-spiral. You take numerical relativity simulations for the late in-spiral merger and ring down. Add some discrete points in parameter space, because we can't do an infinite number of calculations. You combine all this data together in some way, and you interpolate it in some way to get a model out that is continuous in parameters, whatever parameters your model is covering. This relies a lot on numerical relativity, so let me switch back and give you some more impressions of how the field has developed over the last 10 years. In terms of length of simulations, I've already shown the 4 top panels earlier on. This black curve here is the one that made the movie in the post-Newtonian comparison. And for equal mass non-spin, we now have simulations lasting 30 or 50 orbits. The longest simulation to date is about 170 orbits. As Pablo said, that simulation took half a year, but because you always make mistakes and rerun multiple times, the whole research project was more like 1.5 years or thereabouts. Another way of visualizing the progress in the field is the sheer number of simulations. The left-hand side here represents the state of the entire field as of 2009, a catalog of every waveform that has been computed by any group worldwide. About 20 of them, as you can see. And even just a few years further, just the SXX catalog has about 170 simulations. And you need to actually zoom in if you want to see the individual gravitational wave cycles. Many of these simulations are also precessing, as you can see with all these nicely modulated waveforms down here. By now, we're actually talking about thousands of waveforms, mostly by 4 groups. Cardiff and Palmer are underpinning the waveform modeling with the Phenom approach. Georgia Tech and RIT are looking at remnant properties, like in Pablo's talk. And the SXX collaboration is, again, waveform modeling, mostly the EOB&R approach. But some of our waveforms, actually quite many, because they are publicly available, are also used in the Phenom approach. Some records as of simulations: the biggest spin evolved is 0.994. The biggest mass ratio with an appreciable number of in-spiral cycles is 18. There's also mass ratio 100 head-on collisions, I think, by Uli here in the room, and a very brief 2-orbital mass ratio 1 to 100 by the RIT group. And as I said, the longest simulation is this 170-orbit monster. Eccentric simulations and processing fully generic ones are also being done. This is some work by my graduate student, Adam Lewis, where we are doing eccentric, non-equal mass processing systems. So this looks like the Kerr geodesic picture, but this is actually a full numerical relativity simulation. And our goal here were omega theta, omega phi resonances between the up-down motion and the in-out motion. The motivation was that at extreme mass ratios, this actually leads to a strong impact on the gravitational wave phase. So we wanted to see whether we can find these resonances and that impact in numerical relativity. We found the resonances quite fine, 4 to 5 or the 3 to 4 resonance. However, at mass ratio 1/7, we didn't find any discernible impact on the gravitational wave phasing. Well, on the one side, it's great that LIGO doesn't have to worry about it. It's an important point, confirming again that the waveforms for LIGO are good. On the other side, it's a little bit disappointing. Finding actually an impact of the resonances would have been really, really nice. Okay, moving beyond post-Newtonian, I mentioned earlier that post-Newtonian isn't quite good enough for spins and mass ratios. And the leading approach for the in-spiral modeling these days is the effective one-body method. This maps the post-Newtonian inspiral onto a motion of a single body in a non-physical space-time, thus its name. There's a Hamiltonian that comes along with it. The Hamiltonian condenses all the post-Newtonian information in one radial function, A of r. Inspiral is added by hand to the Hamilton's equation by adding radiation reaction terms. And there's a lot of other features. The big benefits for waveform modeling is that this model has the extreme mass ratio limit built in by construction. So it will recover Schwarzschild because this function A is going to the respective Schwarzschild function if you set the mass ratio to 0. And the model also makes it really easy to utilize a variety of non-post-Newtonian information as well. For instance, cell force calculations a few years ago were able to compute periastron advance corrections. And those periastron advance corrections can then be folded back into the EOB Hamiltonian. Or, more important, numerical relativity has been building and is continuous to build these big catalogs of waveforms in various regions of parameter space. The inspiral phasing of these simulations, the gravitational wave amplitudes, are again folded back into the EOB Hamiltonian and into the radiation reaction terms. The way this works is that into the EOB formalism that first of all comes without free parameters, there's a whole host of free parameters inserted in various strategic places. I'm only listing a few here. There's many, many more you can put in. And you can fit those extra parameters to improve agreement with the numerical simulations. And whenever you find disagreement, the usual strategy is to put some more parameters somewhere and repeat. At the end of the day, you also need to think about merger and ring down. And in the EOB model, the merger is basically handled phenomenologically with fitting functions. And then one attaches the ring down modes with frequencies and decay rates obtained from quasi-normal mode calculations, and with initial conditions coming from numerical simulations. So this is overall quite a complicated setup, but it works remarkably well. Here's one example showing you the agreement between the full numerical simulation and the EOB model. The state-of-the-art models are called SUB and RV4 for aligned spin, and SUB and RV3 for the best precession model that currently exists. I mentioned briefly periastron advance early on, and that actually gave rise to another quite interesting, the first time comparison between all three techniques, post-Newtonian, perturbation theory, and cell force. And so what this plot is showing, it shows the difference between periastron advance from the numerical simulation and the other techniques. So numerics is sitting up here at 0, with the red bands being the uncertainty. Post-Newtonian is a little bit away for equal masses and becomes increasingly worse for unequal mass systems. Cell force results is the opposite. They're exceptionally worse for equal masses, and they become better as the mass ratio becomes more extreme, as you would expect. Except one twist that was found here is that the cell force results could actually be made to agree with numerical relativity all the way to equal mass systems by the simple change of re-expanding the cell force results in terms of the symmetric mass ratio instead of the naive M1 over M2 mass ratio. And so that was quite a surprise. It's not well understood. Sometimes the symmetric mass ratio expansion makes cell force results very well working. Sometimes it doesn't. Again, it's only through comparisons with the different techniques you can actually work out where each technique is valid. And sometimes it can be a remarkably large region of validity. The second approach to waveform modeling, and this is a figure where this one should have gone away, is the so-called phenomenological approach. And this is a more down-to-earth approach. It doesn't really take too much account of all the fancy EOB theory in the background. It uses analytical waveforms for the inspiral. It uses fitting functions that are inspired by inspection of numerical simulations for some intermediate regime and for the merger ring down. And then there's a lot of free parameters, betas and alphas, which happen to be functions of mass ratio and spin, floating around there. and those are fitted against order 50 or 100 numerical simulations. The best models to date are called phenom D for aligned spin systems. So this is one in the sequence of phenom A, B, C earlier systems over the last 10 years roughly. And phenom PV2 is the current state-of-the-art processing system. One important aspect of the phenom systems is they are constructed directly in the frequency domain, and therefore they are very, very fast to be used in LIGO analysis. So typically, they are about 2 orders of magnitude faster than the EOB models that I discussed earlier. Here's one example of a phenom waveform, aligned spin, mass ratio 8, quite high spins. Again, as before, very good agreement with numerical relativity. Also, the two models, EOB and phenom, agree quite well with each other. So this is a plot parameterizing the disagreement between the two models. So white is good, colors are bad. There's a lot of disagreement at very small mass ratio. That's the black hole neutron star systems I keep on mentioning as we need better waveforms for. There's also some disagreement at large spins. Chi effective is the sum of the aligned spin components. So if both spins are co-rotating, then the waveform models disagree. And if the antisymmetric spin is large, if one is very large and one is very small, up and down, then again the models disagree. Luckily, perhaps for us so far, the LIGO detections are very nicely in the wide region of parameter space. High mass ratios close to 1, and effective spin parameters near 0 or about 0.25. Perhaps a few more points about precession. I explained earlier that the post-Newtonian gravitational wave phasing is not accurate enough. It turns out the post-Newtonian precession equations are remarkably accurate. These plots show angular momentum and spin precession cones for a few simulations. And they show both the numerical results, the full solutions of Einstein's equations, as well as the post-Newtonian results. And you can't really see any difference. So the post-Newtonian precession equations work quite well. And this is taken into account when constructing the current crop of precessing waveform models. The basic idea is you take your precessing waveforms with the modulations, and after going to a suitable co-rotating frame that is aligned with the instantaneous orbital plane, the spherical harmonic modes become extremely well behaved, no more modulations visible, dominated by the 2-2 mode, 2-1 and 2-0 modes quite a bit smaller. And so the way the current models work is they use analytical prescriptions for the precession, and then in some sense rotate the underlying numerical relativity fitted aligned spin waveform models. Here's a plot that Gabi will be discussing in much more detail later on. What I like to draw your attention to are the red and the blue curves here, which represent parameter estimation with the two models I've just described, phenom and SEOB and R. And you have to look very closely to actually notice that these two curves are on top of each other and give completely consistent results for the typical parameter estimation that LIGO is reporting in their papers. And another separate NR validation has been done for the first gravitational wave detections. For instance, at this point is a gravitational wave injection with all the physics, all the higher order modes, a little bit of eccentricity, and it has been recovered with the standard LIGO parameter estimation techniques. And as you can see, there's no noticeable bias in the mass recovery. There's also no bias in the spin recovery. Having the two very distinct numerical relativity approaches I've described early on, we can also make cross comparisons between those two approaches. That's illustrated here. You're seeing here two numerical relativity waveforms corresponding to the first event, 150914, and they are essentially indistinguishable from each other for all practical purposes. So we really do believe that the waveform modeling part for the LIGO detection is very well under control. 151224 is an interesting system because it's lower mass and therefore a lot longer. That makes waveform modeling a lot more difficult. Another figure that probably Gabriel will be discussing in more detail, the gray bands here are the recovery of the LIGO parameter estimation based on the then best waveform model. To be sure that there's no phasing disagreement creeping into these models, for this system, again, a separate numerical relativity follow-up simulation was run, and that's the red line. And during the in-spiral, red and gray, model and independent simulation, are completely on phase of each other. So this worked very, very nicely. One aspect that's quite neat here is actually the ring down. If you look carefully, you will notice that the ring down, numerical relativity, and the gray reconstruction bands are actually getting out of phase a little bit. And this first puzzled us until we realized that this is actually a feature and not a bug. The numerical relativity waveform that's being plotted here is at the high end of the mass ratios that are consistent for this particular signal. During the in-spiral, the mass ratio doesn't matter because it's only the chirp mass that determines the signal. And so the in-spiral waveform looks perfectly fine. The ring down, however, is more depends on the total mass of the binary. And as you switch a slide along the equal chirp mass contour, the total mass changes. And so over here we have a different total mass and therefore slightly different ring down frequencies. And in fact, it's this disagreement in the ring down that ultimately is responsible for the measurement of the mass ratio in the LIGO events. I should point out finally, or almost finally, a new kid on the block in terms of waveform modeling, and those are the surrogate models. And the goal here is quite ambitious, is to do away with all the intermediate analytical waveform representations at all. So the current best approach relies directly on about 750 simulations. And then it uses a lot of fancy applied mathematics to compress the waveforms into fewer basis vectors, represent these few basis vectors also by a compression in time, and doing a lot of smart choices in interpolating the coefficients of the basis vectors across parameter space, across mass ratios and spins. Doing so, the current state of the art could represent a 7-dimensional waveform model, mass ratio in all 6 spin components, including subdominant modes. And so here, this shows the improvement that you can gain from this type of modeling. The phenomenon AUB models have errors of the order 10 to the minus 1, 10 to the minus 2. Those are dominated by the absence of subdominant modes. Whereas this new model, because it has a lot of subdominant modes, it gets down to 10 to the minus 3 to 10 to the minus 4 in terms of error. Of course, the waveform models are also actively being worked on to improve the, put in subdominant modes. So this is a very promising approach, currently unfortunately limited to only very unambitious mass ratios because it requires a lot of calculations in the background. Eccentric waveforms are beginning to get developed as well. And let me finally point out a few challenges going forward, because I don't want to get across as just being a cheerleader here. The biggest challenge perhaps are the black hole neutron star-like mass ratios, order 1 to 10 or thereabouts. Numerical simulations are much more expensive. Post-Newtonian is much less accurate there. So this is definitely a weak spot presently. And intermediate mass ratio black holes or extreme mass ratio black holes would be even harder. As the SNR goes up, systematic effects will become more important. It's presently unclear whether this already will come in at advanced LIGO design at SNR of 100, or whether we are fine until the 3rd generation detectors and LISA, where SNR is going to be up to 1,000. And with more events coming in, some will be more special. There will be edge-on systems or eccentric systems, and those will also require more precise waveforms. So I'll put up my summary with another nice movie. Basically, black hole simulations have been stunningly successful over the last 10 years. And today we have 2 very well-developed waveform models to underpin today's gravitational wave astronomy. But the big challenge moving forward is to actually push capabilities. Factors of 2 can be done with due diligence, but pushing any capability by a factor of 10 will require fundamentally new approaches, new algorithms, and so forth. Let it be you want to get a factor 10 closer to extremal spin, a factor 10 higher mass ratio, factor 10 longer, or factor 10 higher accuracy. All of these have limits a little bit beyond where we currently are that require new answers. Thank you very much.
All right, I see Bruce is gunning to go there.
So 20 or 25 years from now, we'll have space-based and ground-based detectors that are making observations every 15 minutes or half hour. And what will we be using then to model waveforms? Will we be just, for example, running really fast numerical relativity codes on really fast computers, and that will we be using analytic techniques that were developed from post-Newtonian plus EOB and other methods, or we'll be using things like these surrogate models? What do you speculate will be the model of choice some decades from now?
Okay,
so I'm asking, who's going to win the competition?
Yeah, complete speculation. I think in that regime, where we also have a lot of signals, it will be some of these applied math techniques like surrogate models. And I would be hoping for yet another level of intermediate reprocessing of data, such that you can cross-correlate data directly with some type of filter, which won't be spitting out SNR, but besides SNR, will also directly spit out the parameters of the systems you have.
Yes, Pablo.
In the plot that you saw, you showed the comparison between phenom and EOV. In the dots that they have color, that
Yep.
they didn't agree. Could you tell us how each of them compare to numerical relativity? After all, that is the solution, isn't it? So what I'm after, which one did the better job in that regime?
I realize I put in quite few comparisons to actually numerical simulations. That is because the set of simulations is still quite small. And so almost all of them are being used to fit, and only some of them are being used for independent cross-validations. And in the regions where you see the biggest overlap, the biggest error, so it's color-coded by the errors, is precisely the region where we do not have simulations presently, so we can't even make the numerical relativity to waveform model comparison.
And we have a level near 0.25 and half of a chi effective.
Yeah.
That's numerical relativity.
So we have some, and typically the EOB models are doing better than the phenom models, but they're also leapfrogging each other. So for instance, the SOB and RV2 model was much better than the phenom models for the in-spiral, and so at low masses. But the phenom C, and especially the phenom D model, is much better for the mergers of high spinning systems. And so it turns out the phenom D model now uses SEOB and R as the in-spiral model to improve the in-spiral. And the new V4 EOB model has worked a lot on its high spin treatment. And so generally, the EOB models tend to be a little bit ahead of the curve, but both are quite good.
Yes, one more question up here. Oh.
Just a quick question. In your slide where you were comparing the post-Newtonian approximation to the general relativity, the plots, you said they tend to differ and start showing you differences when you're changing a few parameters. I was just wondering if these parameters are just manifestations of the code, or do they trickle down to some physically relevant parameters?
Oh, that's a very interesting question. Where is this?
It's long back.
I might have too many slides.
It's like halfway through your talk, I think.
That's not particularly helpful.
Sorry.
It's here. That's a very interesting question you're asking. And it's interesting for two reasons. So The difficulty is that radiation reaction comes only in at 2.5 post-Newtonian order. So I actually need to go back to the one slide I have up here. This slide is the, let me zoom in, otherwise you're not seeing anything. This slide is actually showing you the two body dynamics, Newton's law on post-Newtonian theory. So up here you have the regular Newton's law, then you have the V over C squared correction, V over C to the fourth correction, all the way up to V over C to the seventh correction. That's why it is so long. It turns out radiation reaction only comes in at 2.5 post-Newtonian order. So it's this term here, that's the very first one that causes in-spiral. And if you just take these equations, in-spiral comes in at 2.5 order, the equations only go up to 3.5 order, so you have the in-spiral only correct to relative 1pn order. That's not getting you anywhere. It's totally wrong. So the trick that's being used to push things up is called energy balance. And what's being done here is it turns out you can compute the gravitational wave flux to high post-Newtonian order. You can compute the energy of the binary to high post-Newtonian order. And you assume that the energy loss, the change in binary energy, is equal to the gravitational wave energy loss.
Okay. Yeah.
That way allows to push the phasing up to 3.5 relative post-Newtonian order. Mm-hmm. But now there's ambiguities in how to actually use this equation when you're going on that have to do with how you're truncating higher order post-Newtonian terms. If you're doing different truncations, each one of them equally consistent, you get these 4 different lines here. And it's not clear why one of them should be better than the other. Rather, the spread here is the post-Newtonian truncation error and uncertainty.
Okay, I see. Thank you.
All right, I think people need coffee, so if you have more questions, catch Harald at the coffee break, but let's thank him again.